Welcome! In this session, we'll dive into LeetCode problem number 1896, minimum cost to change the final value of expression. This is a fascinating problem that challenges our understanding of Boolean expressions and optimization. Let's explore the problem, analyze key approaches, and work toward an efficient solution. Ready? Let's get started. In this problem, you are given a valid Boolean expression represented as a zero-indexed string called expression. This string consists of specific characters that represent Boolean values and operators. The characters 1 and 0 represent the Boolean values true and false, respectively. The logical AND operator is represented by AND, and the logical OR operator is represented by. Parentheses, represented by, and, are used to group parts of the expression and override the default precedence of operators. The evaluation of the Boolean expression follows standard rules of Boolean algebra. For example, 1 and 1 evaluates to 1, whereas 1 and 0 evaluates to 0. Similarly, 1 0 evaluates to 1, while 0 0 evaluates to 0. Your task is to determine the minimum cost to change the final value of the expression by modifying any 0 to 1 or any 1 to 0. Each change has a cost of 1, and note that you are not allowed to modify the operators or parentheses. The input expression will have a length between 1 and 100,000 characters, so efficiency is important. The output for this problem is an integer representing the minimum cost required to change the final value of the given Boolean expression. To better understand this, let's look at an example. Suppose the input expression is 1 and 0 1. When evaluated, the expression results in 1 and 0 1, which simplifies to 1 and 1, finally giving the value 1. If we want to change the final result of the expression to 0, we need to make some modifications. The minimum cost in this case is achieved by changing the 1 at index 0 to 0. This results in the modified expression 0 and 0 1, which evaluates to 0 and 1, resulting in 0. The cost of this change is 1, which is the output. Now, consider another example where the input expression is 1 1 and 0. When this expression is evaluated, the result is 1 1 and 0, which simplifies to 1 0, and finally evaluates to 1. To change the final value of the expression to 0, the minimum cost is achieved by changing the 1 at index 0 to 0. The modified expression becomes 0, 1 and 0, which evaluates to 0 0, resulting in 0. Again, the cost of this change is 1, which is the output. Let's explore one more example. If the input expression is 0 and 0 0 0, its evaluation proceeds as follows: 0 and 0 0 0 simplifies to 0 and 0, which results in 0. To change the final value of the expression to 1, the minimum cost is achieved by changing the 0 at index 0 to 1. This modification results in the expression 1 and 0 0 0, which evaluates to 1 and 0, finally giving the result 1. The cost of this change is 1, and that is the output. These examples demonstrate how to determine the minimum cost to modify the Boolean expression's final value. To summarize, the input will always be a valid Boolean expression consisting of the characters 0, 1, and end. Parentheses are balanced and used correctly, and the evaluation follows the standard rules of Boolean algebra. You are only allowed to change 0 to 1 or 1 to 0, with each change incurring a cost of 1. There are several edge cases to consider. For single character expressions, the output is always 1 since only one change is needed. For expressions without parentheses, you can directly evaluate the logical operations to determine the required change. Finally, for large expressions up to 100,000 characters in length, your solution must be efficient and scalable to handle the input size within the problem's constraints. To tackle problem number 1896, the goal is to determine the minimal cost required to flip the final value of a Boolean expression. This involves analyzing the logical structure of the expression, which is composed of 1, true, 0, false, and, or, and parentheses that enforce precedence. A straightforward way to approach this is through a brute force method. In this approach, we evaluate the expression's current value, then systematically attempt to change each character, either flipping a 0 to 1 or vice versa, or modifying operators, and re-evaluate the expression to check if the final value flips. The minimum cost among all valid changes becomes our result. However, since this process involves repeatedly parsing and re-evaluating the expression for every possible modification, it leads to exponential time complexity. While this method is intuitive, it's computationally impractical for large expressions due to the significant overhead of nested evaluations. Now, a more efficient way to solve this problem is through an optimized approach that avoids redundant computations. Instead of re-evaluating the entire expression repeatedly, we pre-process it to compute two key costs for each sub-expression, the true cost and the false cost. These represent the minimum cost required to make the sub-expression evaluate to true or false, respectively. To achieve this, we use dynamic programming combined with a stack to handle operator precedence and parentheses. For example, with the AND operator, flipping the result requires changing at least one operand, while with the OR operator, flipping the result means all operands must be flipped. Additionally, the cost of flipping a 0 to 1 or vice versa, as well as changing an AND to or the reverse, is always 1. By traversing the expression with these rules and computing costs for each sub-expression, we can efficiently determine the minimum cost to flip the final value. This approach has linear time and space complexity, making it much more scalable than brute force for larger inputs. The optimized approach is the preferred strategy for this problem because of its balance between efficiency and clarity. By pre-processing the expression and using dynamic programming, we minimize redundant computations while ensuring correctness. The stack-based traversal ensures that sub-expressions are processed in the correct order, respecting parentheses and operator precedence. When comparing the two approaches, the brute force method is conceptually straightforward and easy to implement, but its exponential time complexity renders it impractical for larger inputs. On the other hand, the optimized approach is highly efficient with linear time complexity, although it requires a more intricate implementation involving stack-based parsing and dynamic programming. Given the problem's constraints, efficiency is a critical factor, and the optimized approach ensures scalability while maintaining accuracy, making it the clear choice for solving this problem. In this problem, we are working with a Boolean expression made up of the characters 0, 1, and AND. The task is to determine the minimum cost required to change the final value of the expression by modifying a single character. For instance, this involves flipping a 0 to a 1, or changing an operator like AND to. To achieve this, the solution involves several steps. First, we need to parse the Boolean expression. This involves evaluating the expression while handling nested sub-expressions, which we can do effectively using a stack-based parsing algorithm. For each sub-expression, we calculate two things: the Boolean value, which tells us whether the sub-expression evaluates to true or false, and the minimum cost to flip this value by changing one character. As we traverse the expression, digits like 0 and 1 are pushed onto the stack along with their respective costs to flip. Operators are stored for later use, and parentheses are handled by marking the beginning of a nested sub-expression. When we encounter a closing parenthesis, we evaluate the sub-expression within it using the stack. By working in this structured way, we can handle the complexity of nested expressions step by step. Once we encounter a closing parenthesis, we pop values and operators from the stack to compute the result of the sub-expression. For any two operands and an operator, we calculate the Boolean value of the sub-expression and the cost to flip it. For example, using the operator AND, the result of combining two true operands is true, and the cost to flip this result involves the minimum of flipping either operand or the operator itself. Similarly, for the operator, we compute the result and determine the minimum cost to flip it. This ensures that for every sub-expression, we have both its Boolean value and the cost to change it. Additionally, we handle special cases, such as single-digit expressions where the cost to flip is directly the cost of changing 0 to 1 or vice versa. For deeply nested expressions, the stack ensures that we always evaluate the innermost sub-expressions first, maintaining correctness and efficiency. While the problem guarantees valid input, it is still important to structure the algorithm in a way that handles robustness, such as considering edge cases like empty expressions or malformed parentheses, even if they are not explicitly required. After processing the entire expression, the stack will contain one final result: the overall Boolean value of the expression and the minimum cost to flip it. This cost is returned as the solution. The algorithm leverages the recursive nature of Boolean expressions, where nested parentheses allow us to break the problem into smaller sub-problems. By using a stack, we mimic recursion, making it easier to evaluate and store intermediate results. A critical insight here is the importance of flipping costs. For every sub-expression, the cost to flip depends on whether it is more efficient to flip one of its operands or change the operator itself. By storing these intermediate results as we process the expression, we avoid redundant evaluations, making the algorithm efficient. The use of tuples to store both the value and the cost to flip for each sub-expression ensures that all necessary information is readily available when needed. Together, these techniques provide a clean and efficient way to solve the problem, even for complex and deeply nested expressions. The algorithm's efficiency can be understood through its complexity analysis. The time complexity is O(n), where n is the length of the expression, as each character is processed exactly once. Sub-expressions are evaluated in constant time relative to their size, thanks to the stack. The space complexity is also O(n), as the stack stores intermediate results for nested sub-expressions. To see the algorithm in action, consider the example expression 1 and 0, 1. First, we parse the expression. The digit 1 has a value of true and a cost to flip of 1. Next, we evaluate the sub-expression 0, 1. Here, 0 has a value of false with a cost to flip of 1, and 1 has a value of true with the same cost. Combining these with the operator results in a value of true and a cost to flip of 1, calculated as the minimum of flipping either operand or the operator. Finally, we evaluate 1 in true, which again results in true with a minimum cost to flip of 1. Thus, the minimum cost to flip the entire expression is 1. This example highlights the systematic approach of the algorithm, ensuring correctness and efficiency in evaluating Boolean expressions. Here, we begin implementing the solution using a class solution with the method min_operations to flip. The goal is to determine the minimum number of flips required to change the final value of the given Boolean expression. Inside the method, we define a helper function DFS which will allow us to recursively process the expression. The parameters L and R represent the current boundaries of the expression or sub-expression we are evaluating. If the boundaries indicate a single character, which is either 0 or 1, we treat it as a leaf node. In that case, we directly convert the character into an integer value, and since this is a single digit, it has exactly one way to be flipped. For instance, flipping as 0 results in 1 and vice versa. Next, we initialize min_flip to infinity and val to none, which will help track the minimum flips and the resulting value as we process the expression. We then loop through the characters of the expression within the given bounds. If we encounter a parenthesis, we need to find the corresponding closing parenthesis to identify the sub-expression it encloses. To do this, we use a stack-based approach where we increment the stack for an opening parenthesis and decrement it for a closing one. Once we match the parentheses, we recursively call DFS to evaluate the sub-expression inside and update our pointer to continue processing the rest of the expression. Finally, if we encounter operators like or and, we identify them for further processing. When the operator is identified, such as or and, we proceed to evaluate the left and right sides of the operator. To do this, we use the DFS function recursively. First, we evaluate the left part of the expression, which spans from the beginning of the current range up to the character before the operator. This gives us the value of the left side and the minimum flips required to change its value. Similarly, we evaluate the right part of the expression, which starts just after the operator and continues to the end of the current range. This provides the value and flip count for the right side. By breaking the expression into these smaller parts, we can combine their results based on the operator to compute the overall value and minimum flips for the current segment. This recursive decomposition allows us to handle expressions of any complexity systematically, ensuring that we consider all possible ways to flip the values to achieve the desired outcome. Here, we begin the implementation in Java for the problem. The main function, min_operations to flip, takes the input expression as a string and leverages a helper function DFS to compute the result. The DFS function is designed to operate recursively, processing the expression between the given indices L and R. If the current portion of the expression is a single character, such as 0 or 1, it represents the base case. In this situation, we calculate the integer value of the character, which directly corresponds to its value in the Boolean evaluation. Along with this value, we also return a flip count of 1, indicating that flipping the value is always possible with one operation. Beyond the base case, we initialize variables to track the minimum flips required and the computed value of the expression. These will be updated dynamically as we parse through the expression. The loop begins at the starting index L, and we use it to examine each character within the range, paying special attention to parentheses for sub-expressions. When encountering an open parenthesis, we need to identify the full sub-expression it encapsulates. A nested loop helps us match the parentheses by keeping track of their balance using a stack variable. Once the closing parenthesis is located, we recursively call DFS on the sub-expression inside those parentheses and adjust our position to continue parsing. If the current character is either the or and operator, we split the expression into left and right segments around the operator. The DFS function is recursively called on both segments to compute their values in flip counts. Depending on whether the operator is or and, we calculate the resulting value of the expression. For the operator, the value is true if either side is true, and the number of flips required depends on whether the result is true or false. Similarly, for the AND operator, the value is true only if both sides are true, and the minimum flips are calculated accordingly. The loop then breaks, as we've processed the operator and its operands. This ensures that we progressively build up the solution by combining results from smaller sub-expressions. Finally, we return an array containing the evaluated value of the expression and the minimum number of flips needed to change its result. This completes the implementation of the recursive depth-first search logic. The overall structure ensures that the expression is parsed systematically, with appropriate handling of operators and sub-expressions. By combining the results of these recursive calls, we are able to determine both the Boolean value of the expression and the minimum number of flips required to alter its result efficiently. In this example, we start with the expression 1 is 0. The first step is to parse the expression and understand its structure. Here, the operator is the bitwise or operator, and the operands are 1 and 0. Our goal is to calculate the minimum cost to flip one value or operator to change the expression's final result. To solve this, we use a depth-first search approach. First, we evaluate the left operand, which is 1. Since 1 is a leaf node, it directly represents its value, which is 1. The cost to flip it to its opposite value, 0, is simply 1. Next, we evaluate the right operand, which is 0. Similarly, as a leaf node, its value is 0, and the cost to flip it to 1 is also 1. With these evaluations, we now have the left value as 1 with a flip cost of 1, and the right value as 0 with a flip cost of 1. Now that both operands have been evaluated, we combine their results using the operator. According to the truth table for OR, the result of 1, 0 is 1, which becomes the current value of the expression. To determine the cost of flipping this result, we consider how to change the final value from 1 to 0. This requires flipping both operands to 0, and the minimum cost for this operation is the smaller of the two flip costs, which is min, 1, 1, resulting in a flip cost of 1. With this, we finalize the outputs for this expression. The result is 1, and the minimum cost to flip the result is 1. Moving on to the next example, we consider a slightly more complex expression, 1 and 0, 1. As before, the goal remains to determine the minimum flip cost to change the result. In this new example, the outer operator is and its operands are 1 and the sub-expression, 0, 1. First, we evaluate the left operand of the outer expression. Since it is a leaf node with the value 1, the flip cost to change it to 0 is 1. Next, we move to the right operand, which is the sub-expression, 0, 1. To evaluate this, we first analyze its left operand, 0. Being a leaf node, its value is 0, and the cost to flip it to 1 is 1. Similarly, the right operand of 0, 1 is 1, which also has a flip cost of 1. These evaluations give us the values and flip costs for the inner operands of the sub-expression. With the inner operands of 0, 1 evaluated, we now combine their results using the operator. The truth table tells us that 0, 1 results in a value of 1. To flip this result to 0, we only need to flip one of the operands, and the minimum cost for this is min, 1, 1, which equals 1. Thus, the inner sub-expression, 0, 1, has a result of 1 and a flip cost of 1. Returning to the outer expression, we now combine the left operand 1 and the inner result 1 using the outer AND operator. From the truth table, 1 and 1 results in 1. To flip this result to 0, we need to flip both operands, which requires adding their flip costs, 1 plus 1, resulting in a flip cost of 2. Therefore, the final result of the outer expression is 1, and the minimum cost to flip it is 2. In this third example, the expression is 0 and 1, 1 and 1. We begin by parsing it into its two sub-expressions, 0 and 1 as the left sub-expression and 1 as the right sub-expression. First, we evaluate the left sub-expression, 0 and 1. For the left operand 0, the value is 0, and the flip cost to change it to 1 is 1. For the right operand 1, the value is 1, and the flip cost to change it to 0 is also 1. Combining these using the AND operator, the result of 0 and 1 is 0. To flip this result to 1, we only need to flip one operand, and the minimum cost is min 1, 1, which equals 1. Thus, the left sub-expression has a result of 0 and a flip cost of 1. Next, we evaluate the right sub-expression, 1 and 1. For the left operand 1, the value is 1, and the flip cost to change it to 0 is 1. The same applies to the right operand 1, with a value of 1 and a flip cost of 1. Combining these results with the AND operator, 1 and 1 gives a result of 1. To flip this result to 0, we need to flip both operands, resulting in a total flip cost of 1 plus 1, which equals 2. With these evaluations, we now have the results and flip costs for both sub-expressions. The left sub-expression 0 and 1 has a result of 0 and a flip cost of 1, while the right sub-expression 1 and 1 has a result of 1 and a flip cost of 2. Finally, we combine the results of the two sub-expressions using the outer operator. The left sub-expression evaluates to 0 with a flip cost of 1, and the right sub-expression evaluates to 1 with a flip cost of 2. Using the truth table for OR, 0, 1 results in a value of 1. To flip this result to 0, we only need to flip one of the sub-expressions, and the minimum cost is min 1, 2, which equals 1. Therefore, the final result of the entire expression is 1, and the minimum cost to flip this result is 1. The time complexity of the min operations to flip function is largely influenced by the recursive DFS function, which processes the expression. First, consider how the expression is parsed. The function uses a while loop to traverse the expression between the given indices L and R. During this traversal, each character is processed exactly once. For example, digits are treated as leaf nodes, while operators like and, as well as parentheses, require more complex handling. Parentheses, in particular, involve matching opening and closing pairs using a stack, which is a linear operation relative to the size of the current sub-expression. Next, for each operator encountered, the function makes two recursive calls, one for the left sub-expression and one for the right. This forms a binary recursion tree. At each level of the tree, a linear scan of the sub-expression is performed to continue the processing. These two components, parsing and recursive calls, form the foundation of the function's time complexity. The height of the recursion tree plays a significant role in the overall complexity. For a balanced expression, where operators are evenly distributed, the tree's height is O log n. This is because the expression is divided approximately in half at each recursive step. However, in a worst-case scenario, such as a purely left-associative or right-associative expression, the recursion tree degenerates into a linear chain, with a height of O, n. Now, combining these factors, the time complexity for a balanced expression becomes O, n asterisk log n. This accounts for the linear scan at each level of the recursion tree and the logarithmic height of the tree. For the unbalanced case, where the tree height reaches O, n, the time complexity worsens to O, n squared, as each recursive level still involves a linear scan. These two cases illustrate the best and worst outcomes for the function's performance. The space complexity of the function is primarily influenced by the recursive call stack. During execution, each recursive call adds a new frame to the stack. For a balanced expression, the maximum depth of the recursion stack corresponds to the height of the recursion tree, which is O log n. In contrast, for an unbalanced expression, where the recursion tree resembles a linear chain, the stack depth increases to O, n. Apart from the recursion stack, the function uses temporary variables like stack, sub_val, and sub_flip. These variables require constant space, or O1, for each recursive call. Since this additional space does not depend on the size of the input, it does not significantly affect the overall complexity. Therefore, the total space complexity is O log n for balanced expressions and O n for unbalanced ones, with the recursion stack being the dominant factor in both cases. To compare, a brute force approach to solving this problem would involve trying all possible ways to flip each operator and recomputing the value of the expression. This would result in an exponential time complexity of O2 to the power of k, where k is the number of operators. In contrast, the optimized DFS approach is significantly more efficient. For balanced expressions, the time complexity is O n asterisk log n, while for the worst-case unbalanced expressions, it is O n squared. To confirm this, consider the recursive tree structure. In a balanced tree, there are at most O log n levels, and each level involves a linear scan of the expression, leading to O n asterisk log n. In unbalanced cases, the recursion depth reaches O n, resulting in O n squared. For space complexity, the recursion stack dominates, requiring O log n space for balanced expressions and O n for unbalanced ones. This demonstrates the efficiency of the optimized approach compared to the brute force method. When solving this problem, there are several common mistakes to watch out for. First, ignoring operator precedence is a frequent issue. Remember that AND operator has higher precedence than, so you cannot treat them as if they can be altered independently without considering these rules. Another mistake is mismanaging parentheses. Parentheses are crucial because they dictate the evaluation order of the expression. If you don't carefully track how parentheses group sub-expressions, you might flip the wrong part of the expression and end up with incorrect results. Additionally, brute forcing every character in the expression, whether it's an operator or a parenthesis, is computationally expensive. This approach might work for smaller inputs but quickly becomes infeasible as the expression grows. Instead, you should consider using more efficient methods like dynamic programming or prefix/suffix evaluations. Finally, overcomplicating the solution is another pitfall. Some candidates try to rewrite the entire expression evaluation logic from scratch, which is unnecessary. Instead, leverage well-established tools like stacks or recursion to simplify parsing and evaluation, reducing the risk of bugs and redundant computations. Now, let's address a few more points that are critical for both solving the problem and succeeding in an interview setting. One common oversight is failing to handle edge cases. Examples include simple expressions like 1 or 0, expressions with deeply nested parentheses, or very large inputs. These scenarios can easily break solutions that haven't been thoroughly tested. A key insight for approaching this problem is to understand that flipping the final value of the expression should involve the minimal possible change. Analyze carefully how altering an operator or modifying parentheses affects the entire result. A dynamic programming approach is particularly effective here. By storing the minimum cost needed to achieve true or false values for each sub-expression, you can avoid redundant calculations and achieve better efficiency. To tackle this problem systematically, break it down into smaller parts. Use a stack or recursion to parse the expression and handle parentheses, then evaluate how flipping specific components impacts the result. Finally, keep in mind that interviewers often look for clarity in your thought process. Be ready to discuss the trade-offs between different approaches, such as brute force versus dynamic programming, and explain how you optimize your solution. This problem has connections to several related problems that can help you build a stronger foundation. For instance, LeetCode 227, Basic Calculator 2, focuses on parsing and evaluating expressions while respecting operator precedence. Similarly, LeetCode 224, Basic Calculator, emphasizes handling parentheses and precedence. LeetCode 856, Score of Parentheses, is another useful problem that deals with evaluating nested parentheses. Finally, LeetCode 241, Different Ways to Add Parentheses, challenges you to divide an expression into subproblems and compute all possible results. In terms of alternative approaches, brute force is the most straightforward method. Here, you test flipping every operator and parenthesis to evaluate the resulting expression. However, this is highly inefficient, typically O n cubed, or worse, and impractical for larger expressions. A more efficient approach is dynamic programming, where you compute the minimum cost to achieve true or false for each sub-expression, reducing redundant calculations to achieve a time complexity closer to O(n squared). Another option is a greedy approach, which involves identifying the most impactful operator or parenthesis to flip based on local evaluation. While this method is fast and simple, it doesn't guarantee the optimal solution in all cases. Each approach to solving this problem comes with its own trade-offs. Brute force is easy to implement and understand, making it a good starting point for developing your solution. However, it is computationally expensive and impractical for large inputs. Dynamic programming, on the other hand, is both efficient and scalable. It allows you to optimize the solution by avoiding redundant calculations, but it does require careful implementation to track the states of sub-expressions accurately. Finally, the greedy approach is incredibly fast for certain inputs and can provide quick approximations. However, it does not guarantee an optimal solution, so its usefulness depends on the specific constraints of the problem. Understanding these trade-offs is key to selecting the right approach for the situation and explaining your choices effectively in an interview setting. Make sure to balance simplicity, efficiency, and correctness when deciding on a strategy. Great job following along. Today, we tackled problem number 1896 and learned how to minimize the cost of changing a Boolean expression's final value. Remember, mastering such problems sharpens your algorithmic thinking and prepares you for coding interviews. Thanks for watching. Be sure to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!